So, welcome back students. So, as we basically continued throughout our discussion, and today what we are going to do, we will be trying to do a rapid fire round to basically test your knowledge, and this rapid fire round is basically based on some of the quiz, chemical quiz, and is basically based on small organic molecules and how you can solve those transformation. I gave them name as a retro quiz, which are basically based on retro quiz. Now, during the study this retro quiz, we will talk about different terminologies. Probably you are familiar with this terminology, which is called TGT, the target molecule. Now, I am trying to put some abbreviation which you may not heard it. It is called FGA. FG stands for functional group, functional group, functional group. Any functional group can be called as FG. A stands for addition. So, if your transformation is gives a functional group addition in the target molecule, that is called FGA. And you can also abbreviate different other terminologies. Let us say TF stands for transformation, stands for transformation. Any potential chemical reaction can be called as transformation. RG, RG stands for ring. If your target molecule having a ring is called RG. CH, CH stands for chain. Sometimes if you have a acyclic chain in the molecule is called chain, RG is there. Now, if you say RGD, which stands for ring disconnection, D stands for disconnection. Okay. If you have CHD, so chain disconnection, disconnection. So, these are the common terminologies you can be, we will be often using. TGT, all of you know target. This terminology is called FGI, is called functional group interconversion. Let us say you are having a alcohol, you are making it aldehyde. So, that is basically give you a functional group interconversion. It is called FGI, functional group interconversion. So, there are other terminologies like functional group D stands for functional group disconnection or functional group deletion. So, those are the points. One terminology is probably all of you are not familiar, is called appendage. Now, what are appendages? Appendages sometimes are called to such groups which are basically hanging through a linear chain. Let us say this is a linear chain and this particular group which is hanging through this linear chain is called the appendage. So, CH to CHO which is hanging here is called appendage, appendage. So, appendage are basically good point of disconnection. So, normally we will try to figure it out those different things in our retro quiz or rapid fire quiz. Start the game. At the very beginning we have a molecule which basically you can see it. See the molecule, it is basically a cyclopentane and a cyclohexane based compound. It is a spirocyclic compound. So, and as I said, you start with a visual dialogue with this molecule or visual communication, visual communication. Now, what is said? It said that this molecule is having a spirocycle structure. Spirocycles are nothing basically having a good spirocyclic structure, a cyclic connectivity, good cyclic connectivity. This is point the spirocycles. Okay. Then the functional group content, Fg content is having only a carbonyl group, ketone, nothing else, fine. Eventually, as I said, if you are familiar with certain reaction, this retro will be very straightforward to you. How? The slide says that a pinacol pinacolone rearrangement, PPR. Now, what is PPR? PPR probably all of you know. Pinacol pinacolone rearrangement is a very conventional organic synthesis transformation. Now, PPR is basically a transformation, it is a transformation, and also you can call it as a functional group addition or functional group interconversion, because this is the starting material you are starting with. You do a pinacol pinacolone rearrangement, I will be coming what is pinacol pinacolone rearrangement, and then this starting compound is having a diol functionality, diol, but the final compound you are not having it, you are having a ketone. So, you can call it as a functional group interconversion as well as functional group addition, because a new functional group has been introduced. Okay. So, pinacol rearrangement is a very interesting rearrangement which basically takes part in presence of mineral acid. You subjected this compound is a mineral acid, one of the OH group will undergo elimination by a water, water elimination takes place, and basically you will getting a carbonium ion here. So, this OH we said okay. So, you will be getting a carbonium ion here, and this carbonium ion will undergo 1,2 migration. One of these things will basically migrate. So, this is 1,2 migration, and after 1,2 migration you will basically get a, let us see the structure now. So, this green bond migrates to this carbocation electron deficient center. Okay. And then what you get? You basically get a cyclohexane system and a cyclopentane system with a OH and a electron deficient center. Fine. So, next is simple H plus removal. To neutralize the charge, you will get the target molecule. So, I said this is very simple, because if you are familiar with the pinacol rearrangement, your job is half done or even 90% done. So, pinacol rearrangement is the crucial reaction, PPR reaction is a crucial reaction, or we will often use the terminology transformation. The transformation is the transformation, we will be using it, transformation. And the conventional retro pathway or the retro arrow, this is the retro arrow we often used. You see in the slide here, retro arrow is the retro arrow we often used. Retro arrow is the main thing. Okay. Now, this particular starting material, as I said, this particular starting material, how you can make it? The diol, this diol eventually can be made from a simple commercially available cyclopentanone. You do another retro by putting cyclopentanone. Cyclopentanone, if you react with magnesium, simple magnesium, that will basically give you a radical coupling, and then you will get this diol, which you can find in the standard textbook. So, this is the chief starting material. So, your entire pathway will now having this picture. You start with cyclopentanone, do a magnesium mediated coupling, you get this diol, this is your forward pathway as I am saying. Then you do a pinacol rearrangement, which is PPR, and then finally you get the your target molecule. So, this is the entire pathway, is a 3-step pathway. Your starting material, this is one of the intermediate, and this is the final product, and these arrows are basically forward arrow, but when you write the retro pathway, you start with this, you give a backward arrow something like this, and you come to the starting material. Here you put a transformation which is called pinacol rearrangement, or you can call it FGA, functional group addition. Here is the intermediate. Okay. Again you can call it FGA, because initial starting material having ketone, the intermediate which is having diol, it is a FGA, functional group addition, or even you can call it functional group interconversion. So, this is the simplified version of a retrosynthetic pathway we will try to follow throughout our discussion, and that will basically should not be too much complicated. We will try to exercise this practice throughout our coursework. So, we will try to have a little bit complex molecules. Let us come to a molecule which is bit complex. It is a bicyclic molecule, I said it is a bicyclic molecule, and as I said, this is basically to test your knowledge. Now, if you are familiar with a reaction named as anionic oxycope, this should not be a problem to you. So, I said draw a retro arrow, and now the slide show will basically give you a things. Now, I am not sure whether you are quite familiar with this particular transformation, but it is basically a unique transformation which basically based on a 3,3 sigmatropic rearrangement, which named as anionic oxycope rearrangement, oxycope. So, this is a unique transformation. So, you can call this retro as a transformation based things, or even it is FGA or FGI, because functional groups in the final product and the intermediate has been rapidly changed. Now, what is anionic oxycope rearrangement? It says that anionic oxycope rearrangement is nothing, it is a 3,3 sigmatropic rearrangement. You try to find it out the network, it is a 1, it is a 2, it is a 3, it is a 1, it is a 2, it is a 3. So, anionic oxycope rearrangement is something like this, where you have a O minus, you need to use a base. Okay. Then basically your entire things, this pi, this 1, 2, 3, the sigma bond and pi bond will try to react, and finally, you will basically get a product something like this. So, this is your main structural viewpoint. Yeah. So, basically it is alpha, beta, gamma, delta. So, this kind of compounds you will finally get in this entire pathway. Now, you see here. So, once this it will become O minus here, okay. Then the pathway start taking place, basically having these things come here and this go back here. So, you need to redraw the structure, to get this product. Finally, this will basically give you the target as we said, it is an anionic oxycope rearrangement. Try to practice it in your home or when you have off time. Fine. Now, this intermediate which you have just drawn here is also not commercially available. So, you need to make it. Now, this seems to be pretty simple. You can have some simple reaction by a vinylic magnesium bromide with this ketone. So, simple Grignard reaction, simple Grignard will able to give you this kind of transformation, simple Grignard reaction, Grignard transformation. Fine, this is commercially available, cheap material. Now, this ketone you need to make, we will do another retro. Now, see the retro which was given in the slide is based on a Diels-Alder cycloaddition. Now, what you exactly do? You basically start with a diene, is the 4+2 cycloaddition reaction, or you can say Diels-Alder transformation. It is a diene, and you need a dienophile, which is the main criteria for Diels-Alder reaction. Okay. So, you start with this diene and you do a 4+2 cycloaddition reaction, and eventually what you will get? You basically get a compound we just drawn in this way. Okay. So, it is 4+2 cycloaddition. Now, you need to convert this compound to the corresponding ketone. How you can do it? It basically says that if you can use a aqueous KOH, so eventually this will give to a replacement of the chlorine with the OH as a nucleophilic partner. Now, this compound is a cyanohydrin, which instantly releases HCN, because cyanohydrins are normally unstable, and finally, you will come back or you can generate the parent ketone. So, this is the main way you can generate the parent ketone. So, what are the transformation we used here? We used anionic oxycope, here, and then we also used a Diels-Alder cycloaddition reaction to get this particular ketone, and this ketone is basically very useful as a starting material, and then you can do a vinyl magnesium bromide reaction, which we have already discussed, and then you can anionic oxycope. So, the quiz number 3, or you see this is the target molecule, where you can see the structure of this particular compound is basically this, is a target molecule. Okay. Now, the target molecule, if you give a functional group analysis, it is basically a internal ester, which is nothing, is a lactone. Okay. Is a lactone, we say is a lactone, fine. So, what are the steps basically you want to have it? You want to have a this kind of things. So, initial target molecule I have said this one. So, now I do a retro by putting something else. We put a double bond here. Why I put the double bond, that will be quite clear after some time. So, means that you just need to do a 2 transformation. This is a 4 member ketone. Now, 4 member ketone can undergo a ring expansion reaction to give a 5 member lactone, if you know this transformation which is called as a Baeyer-Villiger oxidation. So, Baeyer-Villiger oxidation will basically give you a 4 member ketone to a parent lactone, 5 member lactone. Okay. This double bond is required, because this double bond we need, you can basically reduce this double bond by palladium charcoal hydrogen to get the target molecule, fine. For the target molecule you do not have a double bond unsaturation. So, next retro is very interesting, and it is all based on the specific transformation, and that should be clear why you put the double bond here. We used a alpha alpha dichloroketone compound as a starting precursor. Now, see that this is known that if you subject this alpha alpha dichloroketone with the zinc, metallic zinc, the dechlorination occurs to give you this target molecule intermediate, which undergoes Baeyer-Villiger oxidation reaction and a palladium charcoal mediated hydrogenation to give you the target molecule. Now, why you have chosen this as a starting material? This is a starting material. We can explain it in the next slide. So, what it says that if you have a intermediate whose structure is something like this, you basically can disconnect in a different way. You can do a disconnection based on a 2+2 reaction, which is not very popular, but still some of the dinophiles give a 2+2 reaction. Now, this compound is cyclopentadiene, which all of us know, cyclopentadiene. This compound is dichloroketene. Ketene are specific compounds which is having this kind of functional group. This is named as ketene. Now, ketene can undergo 2+2 cycloaddition under thermal condition. By simple chemical logic, we know that 2+2 reaction can occur under light, but ketene has a specific molecular orbital alignment which allows the ketene can undergo 2+2 cycloaddition. This information you just keep it as your in your memory. So, then if you undergo 2+2 cycloaddition reaction with ketene, you get this compound, okay. And then you do a dechlorination as discussed earlier, do a Baeyer-Villiger reaction. So, particularly if you do not know this reaction, which is this transformation, probably your entire pathway is not possible. So, that is what I am saying, more and more transformation you know, or more and more knowledge based information you know, you will be quite familiar to design a efficient pathway. So, this pathway basically says like 3-step pathway. You see the pathway is a 3-step pathway. You start with a ketene, start with a ketene, then take the cyclopentadiene as a 1 step, then you do a dechlorination here. Once you get the intermediate, you do a dechlorination here, then you do a Baeyer-Villiger oxidation, and finally palladium charcoal mediated hydrogenation, that basically gives you the final product. So, our next we will be having some further quiz. So, the next quiz, which was basically a similar kind of problem, the target molecule is a bicyclic compound. See its structure, It's pretty simple bicyclic compound. It's a bicyclic compound. Okay. It's a bicyclic compound. Now, a simple chemical analogy, you can devise a retro which will basically will give you a very well known reaction which is named as Robinson annulation or is a Michael aldol reaction. Now, you can basically have a intramolecular aldol version, intra-aldol reaction. Okay. It is a intra-aldol reaction. Now, what is the reaction? It is basically undergoing a this minus will attack to the electrophilic ketone and final dehydration to give you the product, fine. So, you need to basically make this compound. Now, this compound is what? Is a 1, 2, 3, 4, 5, 1, 5 dicarbonyl species. Now, we see its structural features. This compound can easily be synthesized if you have a starting material something like this and a Michael acceptor something like this. So, what is this? The 2 methyl cyclohexanone and it is a methyl vinyl ketone. So, if you subject this compound 2 methyl ketone to a base, normal base like LDA or something like that, you basically have a enol generated by abstracting this hydrogen. Okay. Now, this is basically the nucleophilic point. So, this nucleophile will now attack to this Michael acceptor like this, these things will attack to this Michael acceptor. Both the way you can write, you can put a free carbon ion, you can put a enolate. Now, once this Michael reaction, so Michael reaction is the key transformation, Michael reaction. So, you basically get the product as I drawn here, then aldol. So, the main highlight of the synthesis is transformation. What we used? We used a Michael reaction followed by a aldol reaction, and this entire reaction sequences was named as Robinson annulation. Robinson is the Sir Robinson which who made a significant contribution in the field of organic synthesis, and annulation, annul means forming ring forming reaction. So, annulations are very useful reaction where you have a possibility of forming ring, you can use annulation reaction. This is a simplified version of annulation reaction, but this usually follows a Michael as well as aldol transformation based on the overall pathway. So, we will go back or we will basically continue our discussion with other quiz. There are a couple of interesting quizzes. Now, throughout this entire coursework, we will talk about more of these quizzes. So, throughout these quizzes basically your doubts will be cleared, and whenever some new transformation we are talking about, I will try to provide the mechanism for individual transformations. Let us talk about these things. This is a cyclohexenone based compound. If you see the target molecule is having a cyclohexenone, this is a ethyl group, and the starting material was taken a or proposed a 1,3-cyclohexane dione. Normally, in many cases I will give you the starting material. So, you can basically design the pathway. I said product or target molecule and starting material is this one. Okay. So, the pathway or the transformation what normally we will use here, it is very interesting. You see the pathway, or we will do a forward synthesis here. Sometimes we need to do a forward synthesis. So, take this compound as a starting material. Now, this compound is having a high acidic hydrogens. So, if we treat with simple methanol, this compound will enolize. This compound will enolize and you basically get a these things. Okay. Now, as I said, the target molecule having a methyl appendage or methyl substitution at this here, methyl substitution in this point, methyl substitution in this point. So, that is very important. So, methyl group is here. So, you need to introduce this methyl group in the early stage of synthesis. So, you put a base, and methyl iodide here, that basically give you a methyl thing with a OMe, fine. So, then what you need to do, you basically need to do some important reaction to introduce the ethyl group, and that was the main highlight of the reaction of the entire course. So, okay, the structure was little bit wrong. You can basically have a structure something like this, double bond O, methyl will be here and there is a OMe here, okay, fine. So, now you do a ethyl magnesium bromide to introduce the ethyl group. This is alpha beta unsaturated ketone. So, ethyl magnesium bromide will basically make a attack here to give you a tertiary alcohol. Your methyl is here, fine. Now, this is basically a vinylic ether and you have a quaternary alcohol. So, if you just subject to this compound with a acid, first the vinyl methyl ether will hydrolyze to give you a OH. Now, this OH won't sit idle. What will try to do? It will basically try to undergo some kind of elimination type of reaction to this, and basically eventually water elimination will lead you the target molecule. This reaction is pretty interesting and this is often regarded as allylic transposition reaction, means that this is a allylic double bond. This allylic double bond is basically migrating or transposed. Transposed means changing the position. So, this double bond is coming from here to here, that is why it is called allylic transposition. Now, how it happens is basically you are having O methoxy, you are hydrolyzing it and then this hydrolysis will basically give you the vinylic alcohol OH, which is prone to epimerization, prone to elimination of water molecule, and then you are having this double bond isomerization or double bond transposition, means double bond has changed its original position to another position. So, that is the one of the assignment that you are basically trying to have a new reaction which is quite unique, because you need to know some important reactions. Next one is pretty simple. We will stop today's discussion after having this one. This one I says your target molecule is something like a cyclohexane carboxyldehyde, but what I said you have a prerequisite, you cannot use hydroboration reaction, that basically puts your selection little bit in dilemma. So, what you can think about this? There are many other ways, definitely there are many other ways. Now, we will do a retro, and we devise that if you can have this kind of vinylic alcohol which can instantly tautomerizes to this, fine. Now, this vinylic alcohol how you can get? We will be using a potentially Wittig transformation by starting from a cyclohexanone with a Wittigilite PH3P double bond CHOMe. Now, this Wittigilite can be instantly generated from a compound called methoxymethyl chloride plus triphenyl phosphine. You do a reflux, just do a reflux, you basically will get MEO CH2 PH3 plus Cl minus. You treat with a base, that will basically generate this Wittigilite, and this Wittigilite will react here with cyclohexanone. So, it will react with cyclohexanone, and what we will get? We will basically get a first a vinylic ether, standard Wittig reaction. The vinylic ethers are prone to hydrolysis. You just put a mineral acid, that will basically give a vinylic alcohol which instantly tautomerizes to the corresponding cyclohexandehyde. So, in nutshell, any of this kind of retro, you can basically figure it out something like this. Let us say you have a ring, you want to make this kind of compound. I said this is a ring, means n could be 4 to 7 or 8, I mean 4 member ring, 7 member ring, 8 member ring. The retro will be something like this. You start with corresponding cyclohexanone, which are very cheap, and then you use a Wittig reaction based on this kind of Wittig halide. Now, this Wittig halide is easily available, or you can even make it by starting from a compound called methoxymethyl chloride. It is called mom chloride, abbreviated as mom chloride. So, this mom chloride Wittig, you can use it to get a very nice way of introducing a carboxyaldehyde group, but eventually you are not using a Wittig reaction. That was the prerequisite, I said, sorry, without the hydroboration reaction. We cannot use the hydroboration reaction. Now, if the standard route, I said you can use with hydroboration reaction, then what is the standard route? You start with the starting material, you initial was the retrocess. If you have this starting material, which is a functional group addition, simple oxidation, and then you do a hydroboration starting from this compound, and then you have a Wittig route starting from cyclohexanone. So, this is the standard route. You can basically make your routes available. So, cyclohexanone, Wittig, you get here. You do a hydroboration, means boron THF, you get cyclohexyl methanol. Functional group addition by simple oxidation, let us say chromium trioxide or PCC, pyridinium chlorochromate, or other oxidizing agent, you are coming here. So, that basically, but we are giving a prerequisite in this particular problem. You cannot use hydroboration reaction. Okay. So, if hydroboration reaction has to be avoided, then you can use the mom chloride Wittig, which just now discussed. If says hydroboration can be used, then definitely you can think about the final route, which we have just discussed. Start with cyclohexanone, do a Wittig, get the corresponding exocyclic methylene compound, hydroboration, and then you come back to the oxidation and get the target molecule. So, you do a functional group addition here. The transformation which we used a Wittig transformation. If we use the hydroboration, we use the oxidation. In the original problem, we use simply a Wittig reaction and a hydrolysis. So, that is it. So, those kind of subtle thinkings are essential to devise a pathway and stay focused whatever was required from you. So, that will basically give you the entire pathway. We will probably try to have a similar kind of problem. Let us see how the next problem comes. Next problem, if it comes, then you can discuss. Next problem is a pretty simple one. We will try to give it little bit faster. It is basically a cyclobutane containing compound. We say BNOH CHO. We do a retro, very straightforward. We say that the compounds, if you have a epoxide and a formyl anion equivalent. Now, BN stands for benzyl. This group BN is basically benzyl. It is a benzyl group. Okay. Now, sometimes can you have this kind of species which are called synthetic equivalents? It is basically formyl anion. Now, we will talk those species in the subsequent sections. Now, the synthesis which was devised here, basically we will have similar kind of pathway. If you have a 1,3-diethane derivative with a lithium species, which all of us know, and this can basically give you a ampol species where the charge has been reversed. And if you have a ampolung species which can attack to this epoxide, that will basically give you the desired product after you remove this 1,3-diethane group by a mercury mediated hydrolysis that will give you the final product. So, I am sorry, this is the basically the cyclobutane based product, and finally, the product which is you get BNOH CHO. So, in the next class we will basically talking about some of the again retro quizzes, and then we will then try to deep or submerge into the real problem. Throughout this entire coursework we will talk about this approach. We take some targets and we try to figure it out what are the transformation available. If you know the transformation, we will explain the mechanism. Otherwise, normally try to explain the mechanism for a unknown transformations. I assume that some transformations which you do not know. So, again, okay, see you in the next week. Have a good time.